Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, and we're on Lecture 10, The Astronomical Origins of Our Timekeeping System. So in the last lecture, we saw the astronomical origins of our calendar, and in this lecture, we're going to learn about the astronomical origins in our timekeeping system. So let's start with a simple question, and that simple question is, how many hours are there in a day? If you've watched Lecture 9, you probably know that this is a trick question and that it's not going to be a simple answer. Go ahead and answer it with what you think is the obvious answer, and then we'll come back and we'll talk more about the details. But go ahead and just answer, how many hours are there in a day? All right, welcome back. Well, I hope you typed in 24 because 24 hours in a day is the typical number that we all talk about. However, we have to talk more about the definition of what we mean by a day. Just as we saw in the last lecture that there are many different ways to measure a year. For example, is a year the length of time that it takes the Earth to orbit the sun with respect to the stars, or the length of time that it takes to go from one equinox to the next equinox, called a tropical year? Or even the length of time it takes to go from when we're closest to the sun to when we're closest to the sun again, called the anomalistic year. A day is defined that the length of time it takes the Earth to turn on its axis. But again, we have to talk with respect to what? Because there's more than one way to measure a day. So the 2 days that we're going to be interested in are the sidereal day, which is the length of time it takes the Earth to turn with respect to the stars, and a solar day, which is the length of time it takes the Earth to turn with respect to the sun. So let's talk about why they're different and how the two of them are different. Before I do that, though, I do want to mention that you keep time by the solar day. Time with respect to the sun. Our watches, our clocks are set by a solar time. We'll talk more about that later in this lecture. Interestingly, astronomers, on the other hand, because we're interested in the stars, we keep time according to the sidereal day. If you get the chance to visit McCormick Observatory, you will notice some beautiful case clocks, grandfather clocks, that are hanging at McCormick Observatory. And people will often come up to me and say, well, those are beautiful clocks, but your time is wrong. And the answer is the time is not wrong. We do keep those clocks accurate. It turns out those clocks are measuring time according to the stars and not time according to the sun. Astronomers use sidereal time. And the two of them differ by a little bit less than 4 minutes a day. A solar day is slightly longer than a sidereal day. A sidereal day is about 23 hours, 56 minutes, and 4 seconds. As I said, we set our watches according to the solar day. Why are these two different from one another? Well, they're different from one another because let's look at this diagram right here. And what happens when we talk about the Earth spinning on its axis and coming back 1 day later? What we forget about is the fact that the Earth has also moved in its orbit around the sun. And if we want the sun to come back to where it was before, the Earth has to rotate a little bit more. Let's see how that is. Imagine that you're standing here at this point O, where the observer is. That's what the O stands for right there. So you're the observer standing on the Earth. And you look up and you see the sun and you see some distant star up there in the sky, okay? So there you are standing on the Earth. Now, you might say that 1 day is the length of time it takes the Earth to turn and come back. So with respect to that distant star up there, 1 day later, you are right here. The problem is, although the star is straight overhead, because the Earth has moved in its orbit around the sun, you have to turn a little bit more to get the sun to come back. So if you look here, you'll notice that because the Earth moved over, although the star is back, the Earth has to rotate a little bit more before the sun is high in the sky again. And that difference here is about 3 minutes and 56 seconds every day. That's the difference between a sidereal day and a solar day. To look at this down here in a little bit more detail, we've got this little graphic right here. Here's what happens. Here you are. As the day goes, as the Earth turns and you come back to this point, the Earth is also moving. You come back to that point. That distant star that was straight overhead is straight overhead here, but the sun is not. You have to rotate an extra Turns out it's 1/365th of a day, or about 3 minutes and 56 seconds to get the sun to come back overhead again. So that is the difference between a solar day and a sidereal day. So astronomers, we use sidereal time, and a sidereal clock is divided into 24 hours a day, but each one of those hours is a little bit shorter than a solar day. And you'll see those clocks at McCormick Observatory. One of them right now happens to be down in the rotunda. If you go to the first floor of the rotunda, you will see a beautiful case clock there. That is our Parkinson and Frodsham clock from McCormick Observatory that's on temporary loan to the rotunda. When the university was when the rotunda was first completed, the clock lived in the rotunda there, and the rotunda was actually used for astronomical observations until the observatory was finished. So, all right, a sidereal day is the length of time that it actually takes the Earth to turn on its axis. All right, but we keep time according to the sun. That's why people long ago used sundials. So let's talk about some astronomical concepts that you use every day that you've probably never thought about. One of them I hinted at in one of my earlier lectures, a couple lectures ago, and that is what happens in the middle of the day. So let's talk about the middle of the day, and I think the best way to do this is to bring up stellarium. So you'll be using, well, you've used stellarium now to complete some of the labs, but let me bring stellarium over here so that you can see it. Let me go ahead and full screen it over here. All right, so there's stellarium. What I want to do in stellarium is I'm going to zoom out a little bit so that we can see more of the sky. So now we can see east, south, and west on there. And I want to bring up in stellarium the meridian. So I come over here to the sky and viewing options window, and then I come over here to the markings, and where it says meridian here, I'm just going to click all these boxes. It's going to show us the meridian. It's going to show us the markings on the meridian. So that's good. So the meridian here, you'll remember the meridian runs from due north to due south and goes straight overhead. And what it does is it cuts the sky into an eastern half and a western half. But the most important thing about the meridian is that when the sun and the stars rise in the east and move across the sky, when they are due south here, they are at their highest for the day. So if I move time ahead, let me bring my day and time window up here. If I bring my day and time window up and I go ahead and I move hour by hour, you will see that as the stars and the sun move across the sky, when they are on their meridian, they are at the highest of the day, and then after that they get lower and lower and lower. So the meridian marks that point of the day when the sun is highest. We call the middle of the day, the moment when the sun is on the meridian, is known as solar noon. Now, we'll talk in a minute as to whether that matches noon on your watch or not, but just know for right now that we call that solar noon when the sun is on the meridian. The AM hours, so let me come back to stellarium here for a second. The AM hours are those hours before noon. And those hours, their name, AM, comes from ante meridium. Ante, meaning before, meridium, middle of the day, before midday, or before the sun is on the meridian. As you can see, meridium, middle of the day, the name meridian, that line that divides the sky in half, derives its name from the fact that the sun is in the middle of the sky on that day. That's where AM comes from. You might have always wondered your whole life, why do we divide the day into the AM hours and the PM hours? And the answer is it has to do with sundials. The AM hours were before the sun was on the meridian. The PM comes from post-meridium, after the meridian, after the sun is on the meridian. And that's the astronomical origins of AM and PM. So now we can talk about apparent solar time. Apparent solar time is the time measured with respect to the real sun. That is, we take the real sun in the sky and we measure time by that real sun. So at noon, the sun would be exactly on the meridian. At 1 p.m., that's 1 hour post-meridian, 1 hour after the sun was on the meridian. 9 a.m. is actually 3 hours before the sun is on the meridian. So 9 a.m. would be 3 hours ante-meridium, 3 hours before the sun is on the meridian. Apparent solar time depends on your longitude on Earth. If you think about this little diagram, we've seen this in this semester before. So we've got the Earth rotating here from west to east, and this is a single observer. Don't think of this as 4 different observers right now. Think of this as a single observer. Here's where they are at noon. 6 hours later, here they are at sunset. 6 hours after that, here they are at midnight. 6 hours after that, here they are at sunrise. And 6 hours after that, here they are at noon again. This person, or here you're experiencing a different time of day because the rotation of the Earth is different. That is, this is noon. Now let's think of them as 4 different observers. Let's think of them as one moment in time. So here's somebody at noon, somebody at sunset, somebody at midnight, somebody at sunrise. This person is experiencing a different time because here the sun is high in the sky. It is on the meridian, that line that goes from due north to straight overhead to due south. The sun is on the meridian, so it's noon. But here, the sun was on the meridian 6 hours ago, so this is 6 p.m. And down here, the sun won't be on the meridian for another 6 hours, and so this is 6 a.m. down here. Okay, so if you go to a slightly different longitude here, you measure a different apparent solar time. So apparent solar time is time with respect to the real sun up there in the sky. All right, so there's a problem with apparent solar time, and that's that apparent solar time varies throughout the year. The length of a day varies throughout the year. And this is because the Earth's speed as it orbits the sun is not exactly constant. We're going to see later on in the semester that the astronomer Johann Kepler first figured out exactly how it is that planets orbit the sun, the laws of physics that dictate how planets orbit the sun. And Kepler's second law tells us that when the Earth is closer to the sun, like it is in January, it's moving a little bit faster. And when that's farthest from the sun, like it is in July, it's moving slower. And so in one day in January here, when the Earth is moving faster, the Earth has to rotate a little bit more to get the sun to come back to being high overhead. And when we are farthest from the sun in July and the Earth is moving slower, then the Earth doesn't have to turn as much to bring the sun back. What this means is the problem with apparent solar time is that the length of a day varies. And if you're using a mechanically regulated clock, a clock that has mechanics that are ticking off the seconds, as the days get longer or shorter, you will be constantly adjusting the speed with which your clock runs. So a long time ago, people decided not to keep time according to apparent solar time. They decided to keep time according to mean solar time. Mean in this case means average solar time. A mean solar time is with respect to a fictitious sun, not the real sun, but a sun that moves through the sky at a constant rate. So rather than resetting our watches all the time and resetting our clocks all the time, we use an average solar sun. It's the average length of a day during the course of a year. So, and as I said, the mean solar sun is time kept by a fictitious sun, a sun that moves at a uniform, even rate around the equator rather than speeding up and slowing down like the real sun does. So here's the thing. You've probably had this experience in your lifetime of seeing, I hope you have, had this experience in your lifetime of seeing a beautiful sundial in a garden. And your first thought is, oh, let's go see what time it is. And you run up to the sundial and you look at the sundial, and it takes you a second to figure out the gnomon, which is the tilted part here, and the shadow of the gnomon, and you read the time off the sundial. And then nowadays I would say you look at your watch, but most of you would probably pull out your phone and look at your phone, and you look at the time on your phone and you look at the sundial, and you realize they're different from one another. And one of the reasons they're different from one another is your phone is keeping time according to the average sun, and the sundial is keeping time according to the actual sun. A sundial keeps apparent solar time. Your watch, your clock on your phone, is keeping mean solar time. And the sun is not always on the meridian at exactly noon. We call the time, the moment that the sun is on the meridian, solar noon. But in fact, because the time on your watch and the time on your phone and apparent solar time vary throughout the year as the Earth speeds up and slows down, sometimes the sun is on the meridian early and sometimes the sun is on the meridian late. And there's a difference, or that difference between when the sun is actually on the meridian and when our clock tells us it's noon is called the equation of time. And the equation of time can be as much as 17 minutes. So the actual sun in the sky and your watch can differ by one another by as much as 17 minutes. Okay? So that's one of the reasons that a sundial and your watch will be different from one another. We'll talk about more reasons in a minute as to why they might be different from one another. But just know right now that's one reason that they're different. So now I want you to answer this question in Learning Catalytics. When a sundial in Richmond reads exactly noon, how often does a sundial in Charlottesville read exactly noon as well? Is it every day? Is it once a year? Is it twice a year? Or is it never? So take a few seconds to go to Learning Catalytics and answer this question. When a sundial in Richmond reads exactly noon, how often does a sundial in Charlottesville read exactly noon? All right, let's find out the answer to this one. It turns out that both mean solar time and apparent solar time differ with longitude on Earth. So imagine that you're in Charlottesville and it's exactly noon. Well, if you travel to the east, so imagine we're here in Charlottesville and it's exactly noon. As I travel towards the east, I'm traveling towards parts of the Earth where the sun is no longer high in the sky. The sun had been high in the sky a while ago, but it's no longer high in the sky. And even if I move just a little bit to the east, the sun will appear a little bit farther west in the sky. That is, as I move just a little bit to the east, the sun will already be past its highest point in the sky. And so even if I travel only a few miles east, the sun moves off the meridian. So that means that according to mean solar time and apparent solar time, every different longitude on Earth has a different time. Let me show you this. So let me put some lines up here. So here's this person at noon. This person is experiencing 1 p.m. At this longitude, it's 2 p.m. At this longitude, it's 3 p.m. At this longitude, it's 4 p.m. At this longitude, it's 5 p.m. And at this longitude, it's 6 p.m. So every longitude on Earth has a different time. Now, that's a bit of a problem, right? Because imagine that you want to set up a Zoom meeting with a friend in Richmond, and you say to your friend in Richmond, well, let's meet at 2 p.m. If we didn't do something about this, your friend would have to say, do you mean 2 p.m. Charlottesville time or 2 p.m. Richmond time? Now, as you can imagine, you know that this never happens, right? You've never had to do this in your life, and that's because we fixed this problem a long time ago. So let's talk about why we needed a fix and how we went about fixing this problem. So the reason we needed a fix came in the late 19th century with rapid travel by trains. Interestingly, up until this point, every city in the world kept their own time. And it didn't really matter, right? If you lived in the time of the early, let's say, the early 19th century, so the early 1800s, you lived in the United States at that time, it didn't matter that the time in Richmond was a few minutes different than the time in Charlottesville, which was a few minutes different than the time in New York and a few minutes different than the time in Baltimore. Because to get from Charlottesville to Richmond, the fastest way to get there was to get on a horse and ride, and that would take at least a day, typically longer, to get to Richmond from Charlottesville. So it didn't matter that the time in Charlottesville was a few minutes different than the time in Richmond. In addition, you didn't have a timepiece that you could carry with you that was accurate enough that you would notice that time difference when you got to Richmond. So it turns out that people long ago didn't notice that there was a time difference. They knew there was a time difference, but they didn't care that there was a time difference. The problem was with the advent of railroads, now it mattered. What would happen in the early days of rail travel in the United States was that every railroad kept time differently. Now, the problem with the railroad was everything had to run in synchronicity. Everything had to run on time. And the reason everything had to run on time is if a train was early or a train was late, it could cause an accident. In the mid-19th century, in the mid-1800s, there were many, many train accidents in the United States. As an example of one, here's an accident in Valley Falls, Rhode Island. It was a head-on collision between two trains and killed 14 people. The thing was, these two trains ran on a schedule every day, and they had several minutes to pass one another. But on this particular day, a conductor's watch was off by 2 minutes of time. And what that meant was that rather than the trains being in the right place to pass one another, the trains were in fact on the same track at the same time, and it created a head-on collision that killed 14 people. And that particular wreck was the 12th train wreck in the United States in 1853. So you can see that was just August, and by August there had already been 12 train wrecks. They needed a better way to keep time. And so what the railroads would typically do is they would keep time according to the city in which they were headquartered. So, for example, the Baltimore and Ohio Railroad would keep time on Baltimore time. The New York Central Railroad would keep time according to New York time. Each railroad, throughout the railroad, wherever they were in the United States, kept time according to their home city. So that meant if you were in Charlottesville and wanted to get on the Baltimore and Ohio Railroad, and that they said that the train was leaving at 1:32 in the afternoon, what they meant was the train was leaving at 1:32 Baltimore time. You needed to be at the station before that, and it would be before that, Charlottesville time, because the train would leave earlier than that, Charlottesville time. Now, that was a bit confusing. It would be especially confusing when you got to a large city. And if you got to a place like, say, Philadelphia, where there were railroads based in Philadelphia and railroads based in Baltimore and railroads based in Chicago and New York, they were all keeping different times. You would see different clocks on the wall that had the time in different cities, so that if you had to transfer from one train to another train, from one company to another company, you could look up at the wall and say, okay, according to New York, it's this time, and according to Chicago, it's that time. And if I'm going to get on the Chicago Midwestern train, I need to be there at this time. All of that was very confusing. So in November 1883, the railroad companies decided that they were going to divide the United States into a series of time zones. And what they meant by a time zone was that everyone in that zone would set their watches to the exact same time, even though the actual time, the apparent solar time or the mean solar time differed for each different longitude. They didn't care. Everybody in that zone would set their time to the same time. And that time would be called standard time. So they divided the United States into a series of 4 time zones. And this turned out to be tremendously successful. There was, of course, as you know, Eastern Time, Central Time, Mountain Time, and Pacific Time. And this was so successful in the United States that by 1884, an international conference was held in Washington, D.C. 26 countries attended this, and they decided to divide the world into 24 time zones, with each zone being roughly 15 degrees wide in longitude. Now, the reason for these numbers are pretty obvious. 24 time zones, and there's 24 hours in a day, meant that each time zone was different from the next time zone by 1 hour. There are 360 degrees of longitude, and if we divide it by 24 time zones, we get 360 divided by 24 is 15 degrees of longitude in each time zone. Now, we didn't stick to exactly the boundaries that were defined in 1884 for a variety of political and social and economic reasons. If you take a look at the time zone map, you can see some of the shifts in time zones here. So if you just look at the Eastern time zone here in the United States, you'll notice that some states like Indiana, which should be in the Central time zone, decided to stick with the Eastern time zone. And here's the boundary for between Central and Mountain. And you can see that a bunch of states or pieces of states have stayed on the Central time zone right there. So you can see that the boundaries don't follow exactly. There are other places here where the time zone takes a huge leap. So, for example, the Aleutian Islands in Alaska here, the international date line, which we'll talk about in a minute, jogs around so that the Aleutian Islands are in the same day as the rest of Alaska. And then it bumps out over here so that the eastern tip of Siberia can be on the same day as Alaska. And then some countries don't use time zones at all. China, for example, all of China uses a single time zone. That's really quite amazing considering that China spans 1, 2, 3, 4, 5 time zones. Everyone in China sets their time according to the time in Beijing. And so the time in Beijing is the time read across the country. Well, imagine that the sun rises at 5 o'clock in the morning in Beijing. Well, here it's, if everyone's on the same time zone, the sun won't rise over here until 1, 2, 3 hours later. So if the time rose here at 5 a.m., it won't rise here, and the clock will read 8 a.m. when the time rises over there. Here's a little bit more accurate of a time zone map. I thought the colors were a little easier to see on this one. This one shows it to you a little bit more accurately, but again shows you that all of China is on one time zone. All right, so go back. So those are the time zones. Let's see. I've already said that 24 hours a day, 360 divided by 24 is 15, or 360 divided by 15 is 24. Each time zone, the important thing to remember is each time zone differs from the next time zone by 1 hour. Standard time gets earlier as you travel to the west, and it gets later as you travel to the east. And I think, actually, interestingly, because of television, most of you know this, we all know that if a program comes on at 8 o'clock Eastern, that's 7 o'clock Central. You've probably almost memorized that. You'll see things all the time that says, watch our program, 10 o'clock Eastern, 9 o'clock Central time. You know that when you go to the west, time gets earlier. When you go to the east, time gets later. Well, that creates an interesting problem. If we go to the east and time gets later, and we go to the west and time gets earlier, what happens when we wrap around the world? How can it get both later and earlier? Because if we keep going west and west, it's going to get earlier and earlier. We'll end up someplace on the opposite side of the world. But if we go from here and we get later and later, we're going to end up on the opposite side of the world. So how does that work? How can it be both later and earlier on the other side of the world? To fix that problem, in 1884, the International Conference decided to draw a line down the middle of the Pacific Ocean called the International Date Line. And the International Date Line is where the day of the week changes. As you go from east to west across the line, you gain a day. And as you go from west to east, you lose a day. So let's talk about the International Date Line. Actually, this one probably shows a little bit. Here's the International Date Line right here. What's fascinating about the International Date Line is when you go from east to west across the line, you gain a day. That is, for these South Pacific Islands over here, it's Friday. For these South Pacific Islands, it's Saturday. And the only thing that divides them is an arbitrary line drawn from human beings. They both experience the same time. You'll notice they're both in the same time zone here. It could be 1 o'clock in the afternoon here, and it's 1 o'clock in the afternoon here. But here it's Friday, 1 o'clock in the afternoon. Here it's Saturday, 1 o'clock in the afternoon. As you go from west of the line to east of the line, as you travel eastward across the line, you lose a day. That is, you drop down a day. So it'd be Saturday over here, Friday over here. But keep in mind that these islands that are just on opposite sides of the date line have the same time, right? Because the time is determined by how the Earth rotates. And if this island is facing towards the sun, then that island's facing in roughly the same direction towards the sun. They both have to have the same time of day, but they have different days of the week. And that's just to make the time zones work out. So there's another map that shows the time zones right there. So now I want you to answer this question. I want you to get a little bit of practice using the time zone map. So it is 2:30 p.m. on Tuesday. What day and time is it in Tokyo, Japan? So 2:30 p.m. on Tuesday, what day and time is it in Tokyo, Japan? You'll want to pause right here. You'll want to freeze it on this slide. And what I want you to do is count the number of time zones. Go both east and go west and see if you can figure out what time it is in Japan if it's 2:30 p.m. Tuesday on the east coast of the United States. Okay, take a few minutes to do that. Definitely pause the video here. All right, so let's answer this question. We're going to do it both ways. We're going to go both east and west, and we should get the same answer both ways. So let's see what happens. So let's start right here and say that it is 2:30. Let's go to the east first. So it's 2:30 p.m. Eastern time on Tuesday, right? 2:30 p.m. So this time zone, it's 3:30 p.m., 4:30, 5:30, 6:30, 7:30 p.m., 8:30 p.m., 9:30 p.m., 10:30 p.m., 11:30 p.m. on Tuesday, 12:30 a.m. on Wednesday. Right as we cross here, we go from 11:30 p.m. to 12:30. Because we're crossing midnight as we come to this time zone, we also change the day. So this is now 12:30 a.m. on Wednesday, 1:30 a.m. Wednesday, 2:30, 3:30, 4:30 a.m. on Wednesday. So going to the east, we got 4:30 a.m. on Wednesday. So let's do that again. 2:30, 3:30, 4:30, 5:30, 6:30, 7:30, 8:30, 9:30, 10:30, 11:30, and 11:30 on Tuesday, 12:30 on Wednesday, 1:30, 2:30, 3:30, 4:30 in the morning. on Wednesday. Let's go the other direction, see if we get the same answer. We should. In fact, I have to argue we have to get the same answer because clearly they're not keeping two separate times, or we're not keeping two separate times. So let's go the other way. All right, 2:30 p.m. So remember, it gets earlier as we go to the west. And so this is 1:30 in the afternoon on Tuesday, 12:30, 11:30, 10:30 a.m., 9:30 a.m., 8:30 a.m. So that's this time zone right here, 8:30 a.m., 7:30 a.m. on Tuesday. We cross the international date line. Because we're going from east to west, we gain a day. And so this was 7:30 a.m. and we crossed the line. Sorry, I messed that up, did I? Okay, let's do that again real quick. 2:30, 1:30, 12:30, 11:30, 10:30, 9:30, 8:30, 7:30. That's 7:30 on Tuesday. We cross the line at 7:30 on Wednesday, 6:30, 5:30, 4:30. So we get 4:30 a.m. in Japan. We get the same answer going both ways. And remember, it was 7:30 on this side of the line. It's 7:30 in the morning on this side of the line, but we gained a day as we crossed the line. And so it went from 7:30 a.m. Tuesday to 7:30 a.m. on Wednesday when we crossed the line, and then 6:30, 5:30, 4:30 a.m. So, hey, we got the right answer both directions. Now I want you to go to Google and do a search on what time it is in Tokyo, Japan. And what you're going to find out is that if it was 2:30 p.m. Tuesday, what day and time is it in Tokyo, Japan? You'll find out that it is probably not 4:30 in the morning. You'll probably find out that it is 3:30 in the morning, depending on the time of year that you do the Google search. So why is that? Why is it off by an hour? And the answer, of course, is daylight saving time. We play with our clock. We play with our clock for old reasons. So during the late spring, all summer, and early fall, we set our clocks ahead an hour to have an extra hour of daylight at the end of the day. So this change is called daylight saving time. Now, this was first done during World War I. And the goal during World War I was to conserve electricity, to conserve energy, mostly to conserve fuel, because at that time, most electricity was being generated by burning coal and oil. And so by conserving electricity, you'd be conserving fuel for the war effort. So why do we need this? What happens as the day gets longer? Noon is in the middle of the day. So as summertime and in the wintertime, say, people get acclimated to getting up at 6 o'clock in the morning. So let's say you get used to getting up at 6 o'clock in the morning. Well, as the days get longer, not only do they get longer at the end of the day, but the sun rises earlier. The problem is most of us have this bad habit, or good habit, I would guess, of getting up at the same time every day. So as the sun rises earlier and earlier every day, rather than getting up earlier and earlier, we would get up at the regular time, and we were wasting those daylight hours. So the idea was put forth that everyone should just get up earlier in the morning. But you can imagine what people would say if we said in the summertime, we want you to get up an hour earlier so that you have an extra hour of daylight at the end of the day. People thought that was ridiculous. So we do something, I think, that's even goofier instead. What we do is we change our clocks. We spring ahead in the springtime. We push our clocks ahead 1 hour. We literally just take our clocks, we move the hour hand, and we make it 1 hour ahead on the clocks. And this has the purpose of getting you up an hour earlier every day. And I have to laugh at daylight saving time because we play this silly game with ourselves. If we were asked to get up an hour earlier, we would say, hell no. But when we're told to change our clocks an hour ahead, and that has the effect of getting us up an hour earlier, we're like, okay, we'll do that. But we would never want to get up an hour earlier every day. It's more to do with psychology. It certainly has nothing to do these days with saving energy anymore. During World War I, the vast majority of electricity was used to power light bulbs, lights in people's homes. And that did matter, right? If it was bright longer into the evening, then you would use your light bulbs less. And by the way, I'll come to this thought in a second. Let me finish that thought first. Today, energy generation or power consumption is vastly dominated not by electric lights, but by other things like air conditioning and heating and climate control. And those things, because they change when the sun is up, it doesn't matter whether you're awake or not, we don't save any energy by going on daylight saving time. So today, daylight saving time is this anachronistic leftover practice that we do. It just confuses everybody. It disrupts everybody's sleep cycles. If it were up to me, if you made me king for the day, I would get rid of standard time and I would just keep us on daylight saving time year round. In fact, the European Union has proposed this, that they will get rid of daylight saving time and standard time, and countries in Europe will be able to decide whether they will permanently stay on daylight saving time or permanently stay on standard time. But in any case, that is daylight saving time. We're not really saving energy by doing that anymore. So, all right. When daylight saving time begins and ends has changed by legislation over the years. The most recent legislation that decided this was passed in 2007. So the United States sets our clocks 1 hour ahead on the second Sunday in March and 1 hour behind on the first Sunday in November. So always remember, spring ahead. We spring ahead and then we fall back. Here's the thing. If you look at those months, March, April, May, June, July, August, September, October, November, that's 9 months of the year. Maybe a little bit less than that because it's the first Sunday in November and the second Sunday in March. So sort of like, 8 months in a week of the year. More than half the year, we are on daylight saving time. And remember, we're not changing anything astronomically. One of the arguments that you will hear every now and then, and I hope it's apocryphal that nobody actually argues this, is that farmers are concerned about daylight saving time because they get that extra hour of sunlight. Remember, we're not changing the spin of the Earth. We are not changing how long the sun is above the horizon. All we do with daylight savings time is change the number on our clock. We push our clock ahead by 1 hour. We're not changing the sky. We're not changing the universe. The sun is not up longer. We're just changing the time that our clock reads. And what we're doing is we're fooling ourselves into getting up an hour earlier. So anyhow, I'll get off my soapbox. Back to this. Spring ahead, fall back. Remember that in the spring, we push our clocks ahead an hour on the daylight saving time. That's important because when we were doing this counting, you were probably doing that during a time that we were on daylight saving time. I didn't specify when this was, but when I'm recording this lecture right now, we happen to be on daylight saving time. And so Japan is one of the countries that does not observe daylight saving time. And so in Japan, they would be an hour different because they did not push their clocks ahead. So instead of being 4:30, it would actually be 3:30 in the morning in Japan because they're not on daylight saving time. That's another reason why you ran up to the sundial and you looked at your watch and you looked at the sundial and it was way different than your watch, is probably you pushed your watch ahead an hour in the springtime. And so that's why they were off by at least an hour. All right. There's one way to get around this. We need a time system which isn't confusing, where you're not converting time zones, you're not converting daylight saving time. And there is a time called universal time. It's called coordinated universal time. It's an international time standard. It's just known sometimes as universal time. It's also known as Greenwich time or Greenwich Standard Time. There's all different names for it, but it's based on a 24-hour clock. So there is no AM and PM. Let me repeat that again. There is no AM and PM in Greenwich time. It is a 24-hour clock. So you go 11 o'clock, 12 o'clock, 13 o'clock, 14 o'clock, 15 o'clock, 16 o'clock, or typically they'll say 1,300 hours, that you'll start, you say 900 hours, 1,000 hours, 1,100 hours, 1,200 hours, 1,300 hours, almost made a mistake there, 1,400 hours, 1,500 hours, 1,600 hours. So it's based on a 24-hour clock. Universal time is the current time on the prime meridian, which is right here in Greenwich, England. So the prime meridian is you'll remember the prime meridian, right? It's the definition of 0 degrees longitude. So here's the longitudes running across the top of my map up here. So 0 degrees longitude is the beginning of the prime meridian. The time in Greenwich, England is the time of universal time at a longitude of 0 degrees. So it's currently about 3 p.m. Eastern Standard Time. So it's assumed that it's 3 p.m. Eastern Standard Time in Charlottesville. What is the current universal time and date? And so go ahead and figure out, and let's just say that it's Tuesday again. So let's say that it's 3 p.m. Tuesday Eastern Standard Time in Charlottesville. What is the current universal time and date in Greenwich, England? So pause the lecture here and take a moment to figure that out. All right, now that you had a chance to figure it out, let's see what you got. So first of all, it's important to realize that it's standard time. It is not daylight saving time, so we do not have to subtract an hour off our watch. Our watch is correct in a sense. So we are here in Charlottesville, Virginia. So Greenwich time is 1, 2, 3, 4, 5 hours different. And you'll remember as we go towards the east, it gets later in the day, right? If it's 3 p.m. here, it's 4 p.m., 5 p.m., 6 p.m., 7 p.m., 8 p.m. So it is 8 p.m. and because we didn't cross the date line and we didn't cross midnight, if it was Tuesday in Charlottesville, it is Tuesday in Greenwich, England with universal time. So the answer to this is not 8 p.m. Tuesday, because remember, universal time operates on a 24-hour clock. So it is, in fact, 2000 hours universal time on Tuesday. So the right answer to this one is 20 hours universal time, 2000 hours universal time, Tuesday, 20 hours Tuesday. So that's the right answer to that one. All right, because here on universal time, it is here at 3 p.m. It is 15 hours, 20 hours is the right answer. So it's, sorry, I got confused myself there for a second. It is 1500 hours, 16, 17, 18, 19, 20 hours universal time. Okay. On a quiz, if I asked you a question like this, I am obviously not going to expect you to have memorized the time zone boundaries across the world. If you have to answer a question like this on the quiz, I will give you this time zone map so that you can actually count the hours yourself. I want you to know how to use it, but clearly I'm not going to ask you to memorize the time zone map. So just to put that at ease. All right. This shows you, however, how we can measure longitude on the surface of the Earth. So a while ago, when we were talking about the celestial sphere, I mentioned that it is very, very easy to measure latitude on Earth. All you do is you measure the altitude of the celestial pole in your sky, whether it's the North Pole or the South Pole. You measure the altitude of the pole, and the altitude of the pole tells you your latitude on Earth. And with a small telescope, or even without a telescope, with just some simple instruments, you can very, very accurately measure your latitude on Earth. The problem with the old maps was they had a hard time measuring longitude. And the reason they had a hard time measuring longitude is because as the Earth turns, you need to use time. You need to use time to measure longitude differences on Earth. And back in the 15th, 16th centuries, early 17th centuries, they didn't have good timepieces. So how would they measure longitude on Earth? Well, there were ways like dead reckoning to measure longitude, which is simply you know the direction that you're sailing and you know the speed that you're sailing at. And so from that, you could just calculate how far you've traveled. The problem with that is you don't get your speed exactly right. You don't have a very good timepiece for keeping time. And so the further away you are, the less accurate your longitude is. So dead reckoning is not a very good way to do it. You could wait for an interesting event that happens at the same time the world over. And this is one of the reasons that things like eclipses were very important, that when a lunar eclipse occurs, everybody on Earth is looking up at the moon and they see a lunar eclipse starting. Well, everyone's seeing it at the same time, which means you could measure the local time using a sundial in one part of the world, measure the local time using a sundial or a crude timepiece in another part of the world, and then the difference in time would tell you the difference in longitude. So that was one way to do it. And for example, let's do this. A sundial at your location reads 3 p.m. From listening to the radio, you know that at that very moment in time, that exact moment in time, because radio waves travel at the speed of light, takes them less than a second to get to you from England, you know that it's 10 a.m. in Greenwich, England. What is your longitude on Earth? If it's 10 a.m. in England and a sundial at your location reads 3 p.m., what is your longitude on Earth? So figure it out. Remember that each hour time zone difference corresponds to 15 degrees in longitude. So figure it out. Take a few moments and come right back. All right. Did you figure this one out? So the important thing here is it's 10 a.m. in England, in Greenwich, England. So right here on the prime meridian, it's 10 a.m. In your location, it's 3 p.m. So where are you on the globe? Well, on the globe, you must be further to the east, because if this is 10 a.m., this is 11 a.m. Remember, it gets later as you go to the east. This is noon, 1 p.m., 2 p.m., 3 p.m. At 3 p.m., you are 1, 2, 3, 4, 5 hours different from 10 a.m. 5 hours at 15 degrees per hour means that you are 75 degrees in longitude, because 5 times 15 is 75. So you are at 75 degrees longitude. The question is, are you east or west? Well, the answer to that is you had to go 75 degrees east longitude. So your longitude on Earth is 75 degrees east of Greenwich, England. This shows you how mariners eventually came to measure good longitudes on Earth. They would use this very crude technique of making astronomical observations of the sky to try and find something where they could calculate or read in a book exactly what time, read in a book called an almanac, exactly what time it would occur in Greenwich, England. And then they could measure the local time that it occurred, and that time difference between when it was calculated to occur in Greenwich, England, and when you saw it happen, that time difference was due to your longitude on Earth. And so you could use that to precisely measure your longitude. An interesting story about Thomas Jefferson is he had a lifelong hobby of measuring the latitude and longitude of Monticello. In fact, of wherever he lived, but since he lived most of his life, or a good part of his life, in Monticello, that's where most of his records about measuring longitudes and latitudes refer to. Latitude was easy. He got it almost right away, because all he had to do was measure the altitude of the North Pole in his sky. But longitude was much harder. And although Jefferson had good clocks, his clocks were set to the time at his local location. He had no idea to know what time it was in Greenwich, England. But Jefferson owned telescopes, and Jefferson observed eclipses. And because eclipses and telescopes could tell him when celestial events were happening by calculations that were done in Greenwich, England, he could compare the time that they were predicted to happen, essentially the universal time that they were supposed to happen, and compare that to the local time when they actually happened, and that would allow him to measure his longitude on Earth. Now, this all finally came to an end when accurate timepieces were developed. And if you're interested in learning the story, there is a fantastic book by Davis Sobel called Longitude. I highly recommend this book. It is a fantastic book. And it is about Harrison, the first man to develop an accurate chronometer that could be carried on a ship. Because what you could do is you could, when you left England, set your chronometer, set your clock to the time in Greenwich, England. And then you could sail the world over, and all you had to do was compare the time on your accurate clock to the local time that you measured by the sun, and that would tell you precisely what your longitude was. And all you needed was a clock that was accurate enough that even if you sailed for many months and came back to England, the clock wouldn't be off. The clock would keep accurate time. And Harrison invented his famous chronometer in the 18th century. And it's a long, beautiful story about the invention of this. It turns out that, I'm sorry to say, that in this story, the astronomers, the king offers a reward for someone who comes up with a good way to measure longitudes. And the astronomers decide that an accurate timepiece, an accurate clock like that will never happen. So they develop all these complicated astronomical methods of using the position of the moon with respect to the background stars. The problem with those are they took observations using telescopes, which you couldn't do on the deck of a ship that was rolling up and down. And the calculations were really complicated, and you couldn't expect a sailor out at sea to know the mathematics to do the calculations. And Harrison instead decided to go the separate route, which was to build a simple clock that would do it very accurately. But he had to build an accurate clock, a clock that could maintain accuracy even on the deck of a rocking ship. And Harrison did this and built his famous chronometer. But unfortunately, the astronomers tried to cheat him out of his reward, and Harrison never received his full reward from the king, and I'm embarrassed to say it was because of the astronomers. But that's a great book. Go out and read the book Longitude if you can. Fantastic story about our timekeeping system. And ultimately, as we've seen, our timekeeping system depends on all of astronomy. So that ends Lecture 10. That is done with our astronomical basis of our timekeeping system. In Lecture 11, we will begin the phases of the moon, and we will learn why the moon goes through its phases, and we will build an accurate model for why that happens. So I will see you in Lecture 11, the phases of the moon.